In this lesson, we shall have a discussion on forecasting and estimating from correlated data, and we shall look at a couple of examples, definitions, and some exercises. Now, there are certain learning objectives that we shall take into account as we discuss this in relation to forecasting. It is noted that after having studied this chapter, you'll actually understand how to correlate bivariate data and use regression analysis to make forecasts and estimates for business decisions. These topics are covered as follows. So we're going to first look at the idea of what you call a time series and correlation, the idea of a scatter diagram, the application of scatter diagram and correlation, sale of snowboards. There's going to be obviously part one. We're going to be looking at the coding time series data, coefficient of correlation, the coefficient of determination, and how good is the correlation in this case. We're going to be looking at what we call linear regression in a time series data. And looking at linear regression, we shall be looking at what we call linear regression line, right? And obviously application of developing regression line using Excel, Microsoft Excel, the sale of snowboards. Part two, for instance, we shall be looking at what we call the application of forecasting or estimating using Microsoft Excel, the sale of snowboards. Part three, the variability of the estimate confidence in a focused alternative approach to develop and verify the regression line. Now, the idea of what we call regression, linear regression, and casual forecasting. Application of casual forecasting surface area and house prices. We shall be actually obviously as part of our learning objectives today discuss the idea of what we call forecasting using multiple regression. Okay, now that is very important, multiple regression. So we're looking at multiple independent variables, the standard error of the estimate, the coefficient of multiple determination, application example of multiple regression, supermarket example. The idea of what we call the forecasting using nonlinear regression, polynomial function, exponential function, which I'm looking at what we call the seasonal patterns in forecasting, application of forecasting when a seasonal pattern exists, soft drinks, considerations in statistical forecasting, time zone, time horizons, collected data, the coefficient of variation, market changes, models, and models are dynamic, and obviously the notion of what you call the model accuracy, the what you call the curvilinear or exponential models, selecting the best model. Okay, these are some of the learning objectives in view of what we're going to discuss. So just an overview of these things here. We shall look at a couple of examples that pertain the idea of what we call forecasting and time series correlation. Right. Now, the top we've already discussed. I know that the presentation might be a bit too tiny, but the top we've already obviously looked at. And I would actually like us to look at the notion of just a discussion on correlation, not a new concept, of course. Right, so in other words, it is very key for us to, as much as this presentation is a bit small, I guess, but now the notion of what we call a useful part of statistical analysis is correlation. Right, what is correlation? It is the measurement of the strength of a relationship between variables. Relationship between variables, that's correlation. Right, if there is a reasonable correlation, then obviously we speak of what we call regression analysis. And regression analysis is a mathematical technique to develop an equation that describes the relationship between the variables in question. The idea of what we call the partial use of this part of statistical analysis is that correlation and regression can be used to forecast sales or make other decisions when the developed relationships or relationship from past data can be considered to sort of mimic future conditions. Okay, so, but now we shall be looking at the idea of what we call a time series correlation. And a time series is nothing other than what? It is past data presented in regular time intervals, such as weeks, months, or years, to illustrate the movement of specified variables. Right, so the idea of what you call the financial data, for instance, such as revenues, profits, costs, can be presented in a time series presentation. Right, so obviously the idea of what you call the operating data, for example, customer service level, capacity, utilization of a tourist resort, or quality levels can be similarly shown. Macroeconomic data, such as gross national product, consumer price index, or wage index, or rather wage levels, are typically illustrated by a time series. Right, in a time series, we are presenting one variable, such as revenues, against another variable, time, and this is called bivariate data. Right, bivariate data. Okay, when I obviously look at examples that pertain what we call bivariate data, data that involves just two variables. The notion of what you call a scatter diagram is actually very important in forecasting. And it's not a new concept, but obviously a scatter diagram is the presentation of the time series data by dots on the XY graph to see if there is a correlation between the two variables. Right, the time or independent variable is presented on the x-axis. So obviously, the time, in this case, the time is in years and is shown on the x-axis. And the x-axis also called the abscissa, and the variable of interest, right, on the y-axis, or what you call the ordinate. So we're dealing with the variable of interest on the y-axis, and obviously the abscissa on the horizontal axis, or the independent variable. Right. Now, the variable on the y-axis is considered the dependent variable. So obviously we say y depends on x, or f of x. And these kinds of notations, like somebody writing f of x and or writing even y of x, to actually mean the dependence of y on x, so x itself being independent, being an independent variable, and y itself being a dependent variable. Okay, right, so right, moreover, just to emphasize here, the variable on the y-axis is considered the dependent variable since it is dependent, right, or a function of time, of the time. So obviously you can have a function of the time there. In the case of our time series discussion, right, time is always shown on the x-axis, but yeah, this is very important, always shown on the x-axis, and is considered the independent variable, since whatever happens today, an earthquake or a flood or a stock market crash, tomorrow will always come. The idea of what you call the application of a scatter diagram and correlation, sale of snowballs, just an example here of the idea of a scatter diagram. So we'll look at a scatter diagram in the event of what you call the snowballs part 1. And let us discuss this example of a scatter diagram briefly, as it is just an example. So obviously we consider the information in table 10.1, which is in that table up there. Right, which is a time series, right, for the sales of snowballs in a sports shop in Italy in 1990. So this shows the sales of snowballs, right, in a sports shop in Italy in 1990. You can see year X is 1990, and the sales units sold 60 in 1991. 90 units were sold in 1992. 110 units were sold, and so on and so forth. Right, using in Excel the graphical command, which is the XY scatter. On Excel, Microsoft Excel, we could always discuss that. I'll have to just establish the extent to which you guys are into Excel and its usage in assessments. Right, the scatter diagram for the data from table 10.1 is shown in figure 10.2. So, okay, this is the data we have, and this is the scatter diagram. And we're able to see the scatter diagram for the sale of snowballs. And one can see that, for instance, in 1990, we have 60 of them. So you have 1990 here, and there are 60 of them. So obviously, looking at the units on the y-axis here and realizing that you have those years like 1990, 1991, up to 2005, and we've shown them there. And it's 1990, then 1991, just moving at a step of 1 year per interval. And then now on the vertical axis, you can see the units like at this point, this will be like a 60. So a 60, well, it's actually just below 200 there. And for instance, you have at 1991, you have a 90. So here's 1991, you have the 90 there. 1992, for instance, you have 110. Okay, all these are still below the 200 mark there, because you're moving in steps of 200 on the vertical axis. And you also have that in the year 1990, okay, 1993, for instance, you have a 320. Right, so 1993, you'd have like 320, which is just below 400 and above 200. And then 1994, you have 250. 1994, you have 250. 250 is just obviously just above 200. So this is like 250. And this can be done once again on Excel, and one gets this presentation there. Okay. And obviously up to 2005. In 2005, you really can see the increase in the number of units sold in the spot shop in Italy in over the years. In the year 2005, for instance, you can see 2,400 units were sold, and 2005, 2,400 units were sold. 2005, you have 2,400 units were sold. Okay. So this is the scatter diagram. Now, key to this is the choice of the scales. And here I can see 1991, 1992, and so on. So these were pretty much following successive 1 year step. And then now the units themselves were just increasing quite rapidly from 60 to 90 and up to 2,500 units sold in 2005. And you really can see this is the scatter diagram that obviously one gets. Okay. Now, what then is key is the fact that with this scatter diagram is shown in figure 10.2, and it is our figure 10.2, it shows the scatter diagram. So we can see that it appears there is a relationship or correlation between the sale of snowballs and the year in the sales of increasing, are increasing over time. Note that in the Appendix 2, you will find a guide of how to develop a scatter diagram in Excel. Okay, anyhow, obviously Excel is used to develop scatter diagrams, and that's not a strange thing. And we shall examine the need to have Excel exercises and discussions to enable the Excel familiarity. Okay, right. So having looked at the idea of the scatter plots, we've already seen that with the scatter diagram. Right, there is something then that becomes so important. Right, there's something called coding time series data. And now coding time series data, for instance, very often in presenting time series data, we'll indicate the time period by using numerical codes, starting from the number 1 rather than the actual period. Okay, rather than the actual period, we can begin from the number 1, 2, 3, and so on. And this is called coding, because somebody is going to be saying, okay, but we started in the year 1990 until the year 2005. And now we can use a different method to studied a time series. So in which case, therefore, very often presenting time series data will indicate the time period by using numerical codes. Can use numerical codes, starting from the number 1 rather than the actual period. Right. This is especially the case when time is mixed. Right. Time is mixed alphanumeric data, since it is not always convenient to perform calculations with such data. For example, a 12-month period would be coded as in table 10.2. Let's look at how we could code a 12-month period. Right, this is an example. Like in January, you could say over a period of 12 months, January is the first month, February is the second, up to December the 12th, running through the rest of the months there as usual. So this is especially the case when time is mixed alphanumeric data, since it is not always convenient to perform calculations with such data. For example, we have shown that in the table there. With the snowball sales, data calculation is not a problem, since the time in years is already numerical data. Since the time in years is already numerical data, so the calculation, therefore, data calculation would not be an issue. However, the X values are large and can be cumbersome to in subsequent calculations. Thus, for information in figure 10.3, which is this one here, this is figure 10.3 label up here, gives a scatter diagram using a coded value for X. So, right, coded value for X, we say 1 is the year 1990, 2 is the 1991, 3 is 1992, etc. The form of this scatter diagram in figure 10.3 is identical to figure 10.1. Right, so obviously we can see that now, this is very important. The form of the scatter diagram in 10.3 is identical to 10.1. So obviously, I mean, we have been able to see the scatter diagram that we can see in 10.2, subject to the data in 10.1. Really can see how the dots and the points have been marked here, and the pattern, these dots trace and the points trace, and it really can see that it is, as this says, the form of this scatter diagram in figure 10.3, this one, is identical to the previous one. That is the point we're putting across. Now, the couple of things then, obviously looking at the scatter diagram, but we try to emphasize the fact that the years here, instead of putting a 1990, just put the number 1, just to simplify these, because putting a 1990 is, as this description says, is often cumbersome. I want us to moreover discuss the idea of what we call the coefficient of correlation, because very often, if we suspect there's correlation in relation to what we call regression analysis, you know, somebody would have the regression analysis. We said that if there is a reasonable correlation, then regression analysis comes in. You can see a pattern, then regression analysis comes in. Reasonable correlation, a pattern, then regression analysis comes in. And this is a mathematical technique to develop an equation that describes the relationship between the variables in question. It is a mathematical technique to develop an equation. Right, so we try to develop an equation that's called regression analysis, okay? That describes the relationship between the variables in question. I want us to continue and discuss the idea of what you call the coefficient of correlation. Let's discuss the use of some of these equations that are popular. You might have obviously seen those in class at the moment. Once we've developed this scatter diagram, a next step is to determine the strength or the importance of the relationship between the time or the independent variable X and the dependent variable Y. Okay, we want to determine the strength or the importance of the relationship between the time or independent variable X and the dependent variable Y. Okay, right, the strength, we want to determine that if there's a strong correlation or there's a weak correlation. Right. Right. And the and the two variables. So X is always our independent and Y becomes our dependent. Our measure is the coefficient of correlation, R, which is defined by by the rather horrendous looking equation as follows. Okay, obviously this one is a very popular one, and I'm sure that for two variables, we're going to be, you can even use your usual calculator, your Casio calculator from school, and one can remember that. But this is the formula we use for the coefficient of correlation. So the idea of the coefficient of correlation. Right, so we have and the summation. Xy minus the summation. X, the summation Y, all divided by the giant square root sign. And you have the big square root like this. And you have here and the summation of x squared, the summation of x squared, and the summation of y squared. Just trying to have a repeat of this, but written a little bit big for more visibility. Okay, the coefficient of correlation is R and is written like this. Here n is the number of the bivariate xy values. Okay, the value of R is either plus or minus and can take on any value between 0 and 1. Right. If R is negative, it means that for the range of data given, the variable y decreases with x. Okay. Then R is negative. If R is positive, it means that y increases. Y increases, y decreases. R is positive, R is negative. Right. If R is positive, it means that y increases with x. R is positive, it means y is increasing with x, and the opposite is true there. Right. So obviously now, the closer the value of R is to unity, the stronger the correlation, or the stronger the relationship between the variables x and y. Okay, if it is close to 1, then it means you actually you have a stronger relationship. This approximate R is approximately 1. The coefficient of correlation is approximately 1. Then you have a stronger relationship. A stronger relationship between the variables themselves. R approaches 0. Okay, when? When R approaches 0, it means that there is a very weak relationship between x and y. So this is too small, and R is approximately 0, so you have a weak relationship. At 1, you have a stronger one, and you have a weak relationship. Obviously, I know that this has been seen at school. Right, the calculation steps using equation, for instance, 10, Roman figure 1, are given in table 10.3. Here's table 10.3. So now we shall look at the calculation steps here. Obviously, the Casio calculator for two variables can just quickly do this. But yeah, we shall discuss a little bit of the steps here. All right, using the coded value for the time period rather than using the numerical values of the year. So instead of using 1990, 1991, use the coded one for the year. Right, so that, for instance, you'd have the year, which is 1990, 1991, and so on. Right, and I want us to, however, it is not necessary to go through this complicated procedure. Is the coefficient of correlation can be determined by using the function correl. Once again, this is very important. When doing this here, we might be using this function to say, however, it is not necessary to go through the complicated procedure as a coefficient of correlation can be determined by using the function correl in Excel, the correl function. You simply enter the corresponding values of x and y, where x is either can either be indicated period, provided it is in numerical form or the code value, right? It does not matter which, as the result is the same. In the case of the snowboard sales given in the example, okay, let's look at the snowboard sales. We've seen those in Italy. That study, in the case of snowboard, in the example, R is equal to plus 0.9652. This is close to 1.0, and thus it indicates there is a strong correlation between X and Y because it's close to 1. So there's a strong correlation in the snowball cases. In Excel, the function Pearson can be used to determine the coefficient of correlation. Now, the idea of the coefficient of determination, okay, we have seen the coefficient of correlation, but there's something called the coefficient of determination, which is R squared. Right, we square the R. It's another measure of the strength of the relationship, and we shall discuss that. Okay, let us discuss briefly this table here and this table 10.3. The coefficients of correlation and determination for snowballs using coded values of R. So yeah, we're looking at two things. We're looking at the coefficient of correlation, and that of determination as part of this table for the year X, 1990, 1991, 1992, and so on and so forth. The couple of things that remain very important. Right, so, okay, we continue. Right. Right, so we continue. Just to right, we continue there. Okay. I want us to look at the coefficient of correlation and also coefficient of determination as part of the table. Right, the X is the year 1990, 1991 up to 2005. X coded. So now you have the coding. 1990 is our first year, 1991 is our second year, and 1992. So this is X coded. So X is the original step of the time period. But now we have the coding 1, 2, 3 up to 16. Up to 16 codes. And we have the Y, then now we can see the units sold of the snowballs, of the snowboards. And you're able to see that, okay, 60 snowboards were sold in 1991, which is our year 2, 90 was sold, and so on. And you really can see, we remember that here. But there are totals here, and this is very important. So the total, so now the total, the X coded allows us to code, and because you can code the time, then we can compute the total. So the total becomes the 1 plus 2 and so on up to 16, and there's the sum of everything. So yeah, 1 plus 2 plus 3 plus 11 plus 12 plus 16 is 136. Now there's something that the units sold 60 and so on, and the sum of them is 16,890. Okay, so now we're adding just the units sold to say how many units were sold altogether. If in 1990, 60 were sold, and we add everything. Then now we're finding the product of the coded period times the Y. And they were able to see that 1 times 60 is 60, 2 times 90 is 180, and 3 times 110 is 330. And lastly, we have 16 times 2,400, which is 38,000. We square the X, which is the coded period. We square X, we square 1, we square 2, we square 3. 3 squared is 9, 4 squared is 16, 5 squared is 25, and so on. We square Y. We square 60, we get like 3,600, and we square 90, we get that. So yeah, this is just those particular the coding and how we computed the squares of both the independent variable and the dependent variable. N, it's 16. Right, we've seen that obviously N is 16 because we have 16 periods here. And now we do the n times the sum of xy. Okay, this is xy, and the sum is this one here, which is 203. 1,200, and we actually obviously multiply that the summation of xy by the n, which is 16. So we actually obviously compute these things just a technique, obviously, but yeah, this Casio calculator can do this, and Excel can do this, and you have the sum of the x and the sum of the y. We have n times the sum of x squared, and so on and so forth. And you have now here's the r, which is exactly this. How did you get the r? We use this formula. And then now there is r squared. And r squared is nothing other than the square of the r. So yeah, in other words, you can square this one, which gives us the coefficient of determination when we're getting the r squared. So yeah, I can just do this one here and then square it. Now, this is very, very interesting. But now then we have two things here, the coefficient of correlation we found and the coefficient of determination, which is the square of r. I want us to continue and discuss the idea of what we call the linear regression, the time series data. Between the x and y, for instance, it is, right. Now, since it is the square of the coefficient of correlation, okay, obviously it is the coefficient of determination that this is referring to. Right, so r squared is another measure of the strength. R squared is another measure of the strength of the relationship between x and y. We're speaking about r squared. R squared is, since it is the square of the coefficient of correlation, so the square of the coefficient of correlation is the coefficient of determination. Okay, now let us continue and just look at a couple of coefficient of determination and look at a couple of other results. Okay. Right, where r is can be either negative or positive. We emphasize that it can be either negative or positive. We've discussed that. The coefficient of determination always has a positive value. Further, right, further, since r is always equal to or less than 1, numerically the value of r squared. The coefficient of determination is always equal to or less than r. Okay. The coefficient of correlation. So this is a very powerful statement here. Further, since r is always equal to or less than 1, so r is always equal to or less than 1, numerically the value of r squared, the coefficient of determination, is always equal to or less than r. Okay, the coefficient of correlation. When r equals 1.0 and r squared is 1.0 as well, okay? When r is 1, in other words, you have a perfect relationship between the variables, and r squared is now still 1.0, which means that there is a perfect correlation between x and y. Once again, it means that you have a perfect correlation between x and y. Perfect correlation means that r is 1.0, and therefore the description is you have a perfect correlation. Okay, between x and y. Okay, between x and y. The equation for the coefficient of determination is as follows. Let's look at the right. Okay, the equation for the coefficient of determination is as follows. Yeah, see, here it is. So the coefficient of correlation and the coefficient of determination. And we can see, therefore, just writing it big in case it looks so tiny, is n, the summation of xy minus the summation of x, the summation of y. Okay, we square this. Yeah, we just square the coefficient of what? Of correlation, and we get the coefficient of determination. Very importantly, we remove the square roots, which is this one. You square this one, and the sum of y squared in the summation of y, like so. Now let us continue and have a discussion on this here. I want us to continue and look again Look again at what? Again, we can obtain the coefficient of determination directly from Excel by using the function RSQ. Right. So using the function RSQ in Excel, we can always look at that once again. We can quickly be in a position to determine the coefficient of determination. For the snowboard sales, the value of R squared is 0.9316. Again, for completeness, the calculation using equation 10.2nd Roman figure, 10 and second Roman figure, which is this one here for the coefficient of determination, is shown in table 10.3. Okay, we saw that. We saw that. Right. The table 10.3 where these was, we calculated both the coefficient of correlation and that of determination in that example. Okay, the question we're asking is how good is the correlation? How good is this correlation? So we're going to look at a couple of things. Right, how good is the correlation? So we take note of a couple of things. Analysts vary on what is considered a good correlation. So in other words, analysts take different positions on what a good correlation is between bivariate data. I say that if you have a value of R squared of at least 0.8, which means a value of R of about 0.9, actually the square root of 0.8, which is 0.8944, then there is a reasonable relationship between the independent variable and the dependent variable. There's a reasonable relationship between the independent variable and the dependent variable. Linear regression in a time series data. Okay, once we've developed a scatter diagram for the time series, okay, let us discuss, we're discussing right now the idea of what we call the linear regression in a time series data. Once we've developed a scatter diagram for a time series data, and the strength of the relationship between the dependent variable y and the independent time variable x is reasonably strong, then we can develop a linear regression equation to define the relationship after that. We can subsequently use the equation to forecast beyond the time period given. This is very important. So hence forecasting. So we can subsequently use this equation to forecast beyond the time period given. We can go beyond the time period given. We can go many years ahead of even what the data gives. The idea of what we call the linear regression line, right? So linear regression line is the best straight line that minimizes, okay? This defines linear regression line in terms of what a linear regression line is. What is a linear regression line? Here's the definition. Linear regression line is the best straight line that minimizes the error between the data points on the regression line and the corresponding actual data from which the regression line is developed. The following equation represents the regression line. Okay, with the usual one we saw even in high school, which is the y hat equals a plus bx. Here, a is a constant value, and equal to the intercept on the y-axis. Yeah, this one is called the y-intercept of the a, and the b. So normally we have our usual y hat, which is a plus bx. This is called the linear regression line. Linear regression line. Okay, linear regression line. B is a constant value. Yeah. Yeah, B is a constant value and equal to the slope of the regression line. Okay, this is a regression line and therefore it has a slope, and the slope is B. X is B is our slope, and this one here is nothing other than the intercept on the y-axis. This one is the slope. The B is the slope. X is the time in the independent variable value. So X becomes the time in the independent variable value. Y hat, then what is Y hat in this formula? Y hat is the predicted or forecast value of the actual dependent variable Y. Okay, what is this? So this one is the predicted. Predicted, or what we call the forecast. Right, so y obviously becomes the forecast value of the actual, yeah, is the predicted or forecast value of the actual dependent variable y. Okay, now the values of the constants a and b can be calculated by the least squares method. The question is, what is the a and what is the b? We can use what we call the least squares method using the following two relationships. Okay, we have the two formulas for the a and the b. So a is the summation of this, and b is the summation of that. And let us quickly just rub shoulders with these equations. I know that you might have seen them very briefly there at school, but in class, but let's just because we've seen the formula for the correlation coefficient and the coefficient of determination, the coefficient of correlation and that of determination. I want us to just have a feel of the A symbol, which is the summation of x squared, the summation of y minus the summation of x, the summation of xy. Okay, y'all, this often you don't need to memorize a lot. It is you can capture that on your calculator can mostly be able to do this and give you the numerical values of this, so that here this one is the sum of xy, the sum of x, the sum of y, divided by n, the sum of x squared, the sum of x, and you square that. Okay, what are these things for? They are for studying our and calculating our forecast. Y, the forecast value, or what we call the predicted value, is nothing other than the y hat, which is the same as a plus bx. And our a is this, and our b is that. Okay, so, but now this is very important for us if we are to, when we are to be in a position to determine y, well, y is the predicted or forecast value of the actual dependent variable. So y hat is the forecast. Okay, so we can use the word forecast or predicted value of the dependent variable y, of the dependent variable y. Okay, sometimes we want to focus, we want to get a y that is beyond the data. We can focus using the y hat. There's another approach to calculate b and a using the average of x and x bar and the average of y or y bar using the two equations below. It does not matter which we use, as the result is the same. Okay, so now we really can obviously not be so concerned here, because we can therefore be able to use two formulas, can use the formulas at the top, but we still can decide, hang on, we don't like the formulas at the top. We're going to use the formulas that use x bar and y bar, in which case, therefore, we can be able to say, okay, it means, therefore, at this point, we can use our, tell that our b is the sum of xy minus n xy divided by the summation of x squared n x bar squared. And then from this, we're able to see, okay, this is our b. So we can use, instead of using this formula, we can use this one. Okay, they give the same answer. If we know the x bar, where x bar it's the mean of x, and there now then our a, because we can get our b here, our a therefore is y minus b x bar. Okay, we can get our our A using this formula. Okay, let us continue now because we're looking at what I call the linear regression and time series data. Now I want us to look at the following thing. Okay, you look at 10.4, for instance, the idea of what we call the regression constants for the snowboards using coded value X. Okay, we started with the years 1990 up to 2005, going through 1997 and the rest of the years. We coded them. The first year of ours, we called it, right. Okay. Right, so, right. Right, so, right. Right, so obviously there's something called the regression constants for snowboards using coded value of X. Right, so now this is extremely important. Now, for instance, for the first year, 1990, 1991, 2005, we got the totals of the codes there, 136. And now we actually therefore have the average of the codes X coded. Average of X is 8,5. And we have the Y here, and we got the total for Y, and the average is this one here, which is 1055.6250. And then now we have the XYs, which are the product of the X and the Y. And then we got the total for that, etc. Okay. Now we are just using a different method here because now we're using the averages, just using the averages. But after using the averages, we're interested in the averages of two variables. So we have the average of X and that of Y. So we got the average of X, which is the X bar. That is what we have here. And obviously the average of Y as well, please, here. So we have the average of X and the average of Y. So we come here. Right, so here we got the average of X, which is at the bottom here, and the average of Y, which is at the bottom here. Right, the rest of these are the things we need. The rest of the things we need to calculate the sum of the products, the sum of the XYs minus n x bar y bar, sum of the x squareds, n minus n x bar that. And A is y minus bx. Okay, we're just using this formula now to find the A and the B. Using averages. And then now, okay, so we're going to use both equations. Now, the n is 16, and the n is the number of all the codes, the coded x. And then now we have the sum of the x's, the sum of the y's, the sum of the x squareds. Here we got the total 1.4, and so on. Okay, A using the 10 Roman figure 4, which is minus 435. B using 10 Roman figure 5, 175. X bar is 8.5. Y bar is 10 point, it's like 1055. Okay, now we're gonna use the two equations to find the X. So there's one that uses averages for the B, and there's one that is using. And let's look at the formula. For instance, this one here. Okay, so using this formula here, for instance, you can use it to get B because we already have the average of the X and the Y, and we divide by that. So using the B, we get this one. And now using the formula, this one here, this one, because now we use the formula 6 and then there's formula 7. We can use the formula 7, which is A equals Y minus BX bar. Okay. And that allows us to get the to get the A. So yeah, we got the A and we got the B. Okay. Now, obviously, take note of those things. The sum of the x, the sum of the y, the sum of the x squared, the sum of xy, n times the sum of x squared, the sum of x all squared, n times the sum of xy. Okay, it's exactly this. Right, the sum of x squared, the sum of xy, n times this, n times the sum of x bar squared. Right, so you have the x bar, you have the y bar, and you have n times the sum of xy. Okay, and obviously, I mean, the n times the sum of xy, you can see it appearing here. And then now you have the sum of x, sum of y. Okay, we have the sum of xy, the sum of xy, and then n times the sum of xy, which is this one. So obviously getting all those, and tabulating them is just a way to show anyway that these can be done manually, but instead the case calculator can do it. Now, the calculations using the 4 equations are given in table 10.4. This is the table 10.4. Right, for the snowboard sails using the coded values of x. However, again, it is not necessary to perform the calculations because all the relationships can be developed from Microsoft Excel, as explained in the next section. Okay, so there's no point to sometimes do lots of things. It takes lots of time. You might not have the kind of leisure of time, and therefore Excel is handy. Excel is handy. The application of developing the regression line using Excel, sail of snowboards, part 2. Once we have the scatter diagram for the bivariate data, we can use Microsoft Excel to develop the regression line. To do this, we first select the data points on the scatter diagram and then proceed as follows. In the menu, select of Excel, select chart, select add trend line. Okay, it's just the Excel way of doing it. And select options and whatnot. You can discuss that. But now the final window is shown in actually figure E7. We shall just go to figure E7. Right, okay, we shall go to figure E7, no doubt. Right, so okay, it's part of the appendix. Right, so in other words, then the regression line using the coded values of x is shown in figure 10.4. This one, okay, we're going to discuss the regression line there. Okay, now on the graph we have the regression line written as follows, which is different from a different form as represented by the equation 10 Roman figure 3. This is the Microsoft Excel format. The Microsoft Excel format is this one. In the form of equation 10 Roman figure 3, it would be reversed and written as this. Okay, in the form of the equation 10 Roman figure 3, it would be written as this because they are. So this is the Microsoft Excel format where it is y equals. So obviously looking at how it writes it, because it's like a plus bx, which is the y hat. So you have y hat is a plus bx. So the first one is actually bx plus a. This becomes the Microsoft Excel format. The y hat here becomes the a plus bx. Okay, just repeating the same thing here. Okay, the a plus bx becomes the right. We just remove this one a little bit anyhow, just to have more clearer discussion. We are obviously effectively saying this one is this one by the Excel, Microsoft Excel, and This one here is in the form of the equation. So the equation we wrote it in the form the constant plus bx, constant plus bx. Okay, and then now you have the other one here that is xl. So xl starts with the x term and then the constant. Okay, continue. Nothing more and less. Now, if we have the scatter diagram, we actually obviously now the regression line for the sale of snowboards using coded value of x. Right, so we're able to take a look at this and see and the fact that this is the way it's written, and obviously you really can see that this has used the Excel, Microsoft Excel format of using the x term first and then the constant, and therefore you have the coefficient of determination r squared. The regression line for the sale of snowboards, this is the regression line has been drawn. However, the regression information is the same, where y is y hat, and the slope of the line b is 175.3971. And A, the intercept on the y-axis is minus 435 point that, okay, it's this one, that's the A. And the B is 175.39. These numbers are the same as calculated and presented in figure right here, in figure 10.4. Okay, there, they are there in figure 10.4. The slope of the line means that the sale of the snowboards increases. Okay, now this is very important. It is just a discussion on what this equation means. So if you are to write this, which is y is the same as y hat, you can write it y hat. So we're writing the Excel format 175.3971x minus 435.2500. Okay, so we can do like that, but I said already y and y hat are the same. Okay, it's useful for forecasting and to or as a prediction there. But I want us to discuss the significance of these values. What does the 175 mean in relation to the slope of the line? And right, these numbers are the same as calculated in 10.4 above. The slope of the line means that the sale of snowboards increases by, okay, the sale of snowboards increases by 175.3971, say about 175 units. So the sale of snowboards increases by 175 units per year. The intercept, so it increases by this amount. So the slope, so it increases by approximately 175 units of snowballs every year. Okay, because you can see that the snowballs with 60 boats sold, and then 2,400 were sold after many years. So now we can see that there was an increase in the sales. The business was booming. There was growth in the sales. More snowballs were sold, but there was an increase of 175 on average per year. All right, so right. Okay. Right, we continue. Okay, continue. Just we'll continue quickly. Okay, yeah, just let's discussing this. Okay, let's continue, please. The intercept A, what does the intercept A means? This thing here, what does it mean? Because now if you say it is Bx plus A, what does it? So this we say that it means that there's an increase because it's positive there. It means that there's an increase. The number of sales increases by 175 per year. The intercept A means when X is 0, the sales are these. When X is 0, the sales are these. Okay, the sales are these. So now, very interesting. I mean, if you, when X is 0, then you're discussing sales which are minus 435.250. What is this? Negative sales? Okay, we're discussing that, which has no meaning for this situation. Exactly what he's saying. So now, if X is 0, then you're speaking of a negative number of sales. No meaning whatsoever for this situation. The coefficient of determination, which is 0.9316, which appears on the graph, is the same as previously calculated, though note that Microsoft Excel uses uppercase R squared. So we're noting that Excel, if we're going to discuss it, if you guys are discussing it today in class, if you need to learn it, it uses capital R rather than the lowercase r. So yeah, Excel uses capital R, where the value of A is negative, but the slope of the curve is positive. Right, where the value of A is negative, but the slope of the curve is positive. Can see the value of A here because this thing is y equals bx plus A. So the value of A is negative, yet the slope is positive. Okay. It is normal to show the above equations for this example in the form y hat. It is normal to show it in the form y hat rather than y hat equals minus 435 that. That is, avoid starting an equation with a negative value. The regression line using the actual values of the year is shown in figure 10.5. The only difference from the only difference from 10.5 from figure 10.5 is the value of the intercept A. This is because the values of X are the real values and not coded values. Okay, so we know that the figure 10.5. Right, so obviously these ones are the real X values here. They're not the coded ones. And we're able to see clearly here. So this is very important for us. We're able to see the difference between the actual graphical representation with the coded values of X and the uncoded ones. And you can see that it is between this was 1990, 1991, then 1992. Between 1991 and 1992, you can see there was a cut there. So between 1991 and 92, but obviously here we're using the real values. But also, we can see that the differences in the values themselves, it's 175 here. And obviously here the slope is still 175, but you can really see the difference in the fact that this one is 435 point that. And here now it is y, just y hat, 175.3971x minus 349. Okay, then 300, 0, 0, 0. Okay, with the decimal comma here, you can use the decimal comma just to mean a separation of the digits, but it's not a decimal. The decimal point is this one. So you can really see, I mean, the difference in the coded X values and the original ones. Snowboards for 2010. Right. For instance, we enter the function menu x value 2010 and the given values of x in years and the given value of y in the table 10.1. This gives the forecast value of y of a, okay, this is very important. So if you're gonna do 2010, view this as a y of x 2010, because now we're forecasting because this one is up to 2005. Excuse. Right, 2005, and then we can focus 2010, and now say we go outside this, we go beyond this. This was up to 2005, but you can focus. We want to know what the sales are gonna be of the snowboards in 2010, in the year 2010. So we put 2010 here like that. Okay. 2010 minus 349,300. 1, 2, 3, 4. Okay. This resource claims that this gives the forecast value of, you need to check this one, 348 right units, meaning that in 2010 we're gonna have this unit sold. Okay, I believe that this is correct. Yeah, but you can use a calculator to check that. So that when you put the 2010 here, it gives this number of sales. But obviously we are focusing here and we are trying to check and see that indeed we have exactly 3248 units is there. Okay, we continue. This gives the forecast value. Alternatively, we can use the coded values of X that appear in the second column of table 10.2. Okay, you can use the coded ones. If you don't want to use the original ones, you can use the coded ones. And the corresponding actual data for Y. If we do this, we must use a code value of the year 2010, which is, in this case, 21. Yet 2005 has a code of 16. 2005 is a code of 16. We saw that because a code of 1 is 1990. Yeah, 1990 has a code of 1. 2005 has a code of 16. Okay. 2005 has a code of 16. That's year 2010 will have a code of what? Okay, so if we go on here, 2005, and then we proceed to the year 2010, what code is 2010 going to have? So it's 5 years difference, and this guy just discussing that. So which means the code is going to be 16 plus 5, which is 21. Note that in any forecasting using the series the series, the assumption is that the pattern of past years will be repeated in future years. Okay, this is very important. Note that in any forecasting using time series data, the assumption is that the pattern of past years will be repeated in future years. Pattern of past years. Right, so in time series, right, so in time series, we assume that the pattern of past years will be repeated in future years. So yeah, we rely on the patterns and we say the pattern, if this was the pattern in this, then we can use it to predict for the future. Right, okay, let's just discuss a bit what this says, which may not necessarily be the case. Also the future, okay, we're saying the assumption is that the pattern will, yeah, which may not necessarily be the case. It may not be. The pattern can change in the future. That's what we're saying. Also, the future, also the further we go in time, the less accurate will be the forecast. The future we go in time, the less accurate will be the forecast. So if we go many years, their forecast will be less accurate. Right. Also, the future we go in time, the less accurate will be the forecast. For example, a forecast of sales for the next year will be reasonably reliable. For the next year is more reliable than in 100 years. Because now if you have a pair of shoes now that are selling now, the shoes that are selling now for the youngsters are the Air Force. So the Air Force and the All-Stars are selling, but now in 100 years, somebody might not even look at the Air Force or the All-Stars. They might forget about those things. For example, a forecast of sales of next year may be reasonably reliable, whereas the forecast 20 years from now would not. Okay. We have that. We have that. The variability of the estimate. The variability of the estimate. So in chapter 2, we presented the sample standard deviation. All right. So in chapter 2, we presented the sample standard deviation S of data by the equation. Okay, yeah, never mind that the chapter 2 thing, but this one is known. Okay, so we are looking about the sample standard deviation. So the sample standard deviation is written like this. This is very, very important for us. So now there's something called the sample standard deviation. Right, so something called the sample standard deviation. And there's something called the population standard deviation, which is different. So so just right here, the sample standard deviation, just to make sure you can use this formula in calculations. Right, this simple. The sample standard deviation. Right, the sample standard deviation is the square root of the variance, and it becomes the square root of the sum of the x minus x bar squared divided by, okay, and then we divide n minus 1. This is a simple standard deviation because there's a population standard deviation where it's n, but for the sample, then it's n minus 1 in the denominator. Something to just note here. Okay, I would like us to look at the fact that the standard deviation is a measure of the, okay, what is standard deviation? This is very important. It's a very important opportunity to look at how literature describes standard deviation. How literature describes standard deviation. Okay, we're going to use calculators and Excel. We need to just do these calculations in the shortest way possible. But the standard deviation is a measure of the variability around the sample mean. It's a measure of the variability around the sample mean, x bar for each random variable x. In a given sample size n, whether a deviation of all observations x about the mean x bar is 0. Equation 2, which is Ix, or the summation of the x minus x bar. The summation of the x minus x bar. The standard deviation is a measure of the variability. What is standard deviation? Standard deviation, is the definition, is the measure, or is a measure of the variability around the sample mean for each random variable x in a given sample size n. Okay. Further, the deviation of all the observations x about the mean is 0, which is equation, this one here, or this. Okay, so yeah, if you were to consider that the deviation of all observations is 0. Okay, moreover, in a similar manner, a measure of the variability around the regression line is the standard error, or the estimate S, and is given by this. So this is something called the standard error. So now the measure of the variability around the sample mean is this one. Measure of the variability around the sample mean is this one, which is the sample standard deviation. Measure of the variability around the sample mean. But there's also a measure of the variability around the regression. Around the regression, we are using the formula, the standard error. And the standard error is the square root of the summation of y minus y hat squared divided by n minus 2. which is this one here. Okay. Okay, now, for example, here n is the number of varied data points, x and y. The value of s for standard deviation has the same units of dependent variable y. The denominator in this equation is n minus 2, or the number of degrees of freedom rather than n minus 1 in equation that. In equation 10, 8, 2 degrees of freedom. So we shall discuss this idea of the degrees of freedom here, and it's something that had to be obviously sort of spent time on in the previous discussion in the sections you're looking at. Right, so here we are really saying the standard error. Right, so the idea of the standard error, which is the measure of the variability around the regression line, is the standard error of the estimate. Okay. Here n is the number of bivariate data points x and y. The value of SE has the same units of the dependent variable y. The denominator in this equation is n minus 2, or the number of degrees of freedom, rather than n minus 1 in equation that. Right, in equation 10 and 8, 2 degrees of freedom are lost because two statistics A and B are used in regression to compute the standard error of the estimate. Like in the standard deviation, the closer to 0 is the value of the standard error, then there is less scatter or the deviation around the regression line. Okay, so this is very, very important. Very, very important. I want to mention that the closer, this point here, the closer to 0 is the value of the standard error. So if this one is closer to 0, it's like approaches 0 with the standard error, then there is less scatter or deviation around the regression line. So if this is like almost 0, it means there's less scatter around the regression line. If this is the case, this translates into saying that the linear regression model is a good fit of the observed data, and we should have reasonable confidence in the estimate, or forecast made. The regression equation is determined so that the vertical distance between the observed or data values y and the predicted values y hat balance out when all data are considered. Thus, analogous to equation 2, right? This means that you'd have that this would be the case. So in other words, the regression equation is determined so that the vertical distance between the observed data values and the predicted data values, right, balance out when the data are considered. Thus, analogous to equation that, this means that with that. Okay, I want us to have a discussion on the applications of Excel a little bit on this. Very briefly. Again, we do not have to go through the stepwise calculation, but the standard error of the estimate together with other statistical information can be determined by using in Excel function what you call the linest. To do this, we select the cell block of 2 columns by 5 rows and enter the given x and y values and input 1 both times for the constant data. Like the frequency distribution, we execute this function by pressing simultaneously on Control Shift Enter. Okay, we shall discuss that. But the statistics for the regression line for the snowball data are given in 10.5. Okay, 10.5 there. A discussion on this particular table 10.5. The explanations are given to the left. We shall look at those. Here are the explanations to the left of this, or rather to the left and to the right of each column, right? Those that we have discussed so far are highlighted, and also note in this matrix that we have again the value of b, the slope of the line, the value of a, the intercept on the y-axis, and the coefficient of determination r squared. We also have the degrees of freedom, or n minus 2, right? The number, or rather the other statistics are not used here, but they're measuring, or their meaning in the appropriate format is indicated in table E3 of the appendix. Okay, let's just have a brief discussion on the table 10.5 where we look at the statistics of for the regression line. B, which is the slope of the regression line. Okay, we saw that the slope of the regression line was exactly 175 point that, but we saw that A was actually minus 435. We saw that, which became the value of A, and this is the intercept on the y-axis. But also, which is the r squared, which is the, right, the coefficient of determination is r squared, and you saw r squared to be this. Okay. And then now we also have the standard error of the estimate. Right, so the standard error of the estimate is exactly this, and this is the formula for the standard error. The degrees of freedom, which become n minus 2, the degrees of freedom. Obviously, we saw why degrees of freedom are labeled as 14 here, because with n minus 2, but n is 16 for the coded data, and therefore is 14. So we're 14 degrees of freedom, and therefore we are able to compute the rest of these statistics. Right, we computed, for instance, the idea of the, just one second, there's something I need to show here. To show here for the 90. Okay. Something I need to show, which is the 1055. Just one sec. Forgetting something here. Right. Okay, I'm sure we shall get to that. Okay, something more I wanted to mention. Right, so, but let's first discuss the idea of the confidence in a forecast. In a similar manner, for instance, now discussing the idea of what we call the confidence in a forecast. How to determine confidence in a forecast? If we can forecast many years ahead, how can we determine the confidence in a forecast? In a similar manner to confidence limits in estimating presented in chapter 7, never mind the chapter there, we can determine the confidence limits of a forecast. Okay, we shall discuss the idea of what we call the confidence limits. Confidence limits of a forecast. Confidence limits of a forecast. If we have a sample size greater than 30, then the confidence intervals are given by that. Then the confidence are given by these. Okay. What is this? Okay. Like we're saying, in a similar manner, to calculate the confidence limits, or rather, yeah, in a similar manner, to confidence limits, I mean, estimating the precedent that we can determine the confidence limits of a forecast. If we have a sample size greater than 30, then the confidence intervals are given by these. For a sample size greater than 30, then the confidence intervals are given by these. For a sample size where this S is a standard error, and obviously this is the forecast or the predicted value. And obviously we are saying that for a sample size greater than 30. Okay, just mentioning that for a sample size greater than 30. So we use this for sample size greater than 30. That's when we can be able to determine the confidence limits of a forecast. Right, I want us to continue to have a brief discussion about table 10.6, but with sample sizes no more than 30. There are smaller sample sizes that are less than 30. We use a student T relationship, the T relationship. We use it for those sample sizes that are less than 30. Less than 30. We use a T relationship, and the confidence limits are y hat, which is plus or minus TSE. For our snowboard sales situation, we have a forecast of 3,248 units for 2010. We saw that one. To obtain a confidence level, okay, we use that one for 2010. We calculated it, but we're then going on to say, to obtain a confidence level, we use a student T relationship, because obviously we're dealing with a sample size is no more than 30. So, and obviously we had 16 there. It's sort of the sample size. The sample size n equals 16. Okay. So it's less than 30, and therefore we're going to use the student T relationship of the, and then we actually obviously put the T there and multiply that with the standard error. But this one, or with the Z, what I wanted to say here. Right, the one with the Z here is used for the sample sizes that are at least 30, greater than 30. Okay. So, right, for the snowball sales situation, we have focused of this one. For 2010, we saw that one. To obtain the confidence level, we use the student T relationship. Right, since we have a sample size of 16, a sample size of 16. Right, for the 90% confidence limit, using the function TNV, like teen V, where the degrees of freedom are given in table 10.5. Okay, we saw the degrees of freedom there, n minus 2. Okay, we continue. All right, degree A are given there. Okay, the value of T is 1.7613. Then using equation 10 and the standard error from table 10.5, the confidence limits are as follows. The lower limit is, okay, obviously we're using the student one, so we're going to use the lower limit and then the upper limit, lower limit and upper limit. So the lower limit, for instance, is going to be, so the lower limit, you use the minus, so it's going to be y hat minus TS standard error, and then there's something called the upper limit. For the student T relationship, the upper limit is, you take the plus. Okay. Okay, there's something more obvious we're gonna say there, because you already know for 2010, for the year 2010, we did it together and we said we can use a calculator to just verify this value, but it came down to 248 if we put it into the regression line. And then now we can use it here, 3248 minus, okay, and now obviously the value of t is 1.73. Right, so, and the, right, so the value of t is actually exactly that one. Right, it is exactly 1.7613. Okay, so if the value of t is exactly 1.7613, we multiply t by the standard error. We can use we saw the standard error formula, and we're told we can check with the calculator, etc. But it's 234.1764. Okay, and then if we do that, the lower limit is going to be 2836. Okay, there's a decimal, there's a comma here, but this is sort of the American way of writing thousands with the comma. It's not our decimal South African system there. So yeah, so the lower limit is going to be this. And then now the upper limit is going to be, you put everything here, the y hat 3248, the t is 1.7613, and the standard error is okay, the standard error is 243.1764, which is 3.361, like that, like that. Exactly that way. Okay. Okay, we continue. We continue. Okay. Okay. Okay, we continue, please. Okay. So we continue. Right. So thus, to better define our forecast, we could say that our best estimate of snowboard sales in 2010 is this. Okay, because this is the upper limit, which is the 2,836. In the upper limit, lower limit is 2,836. The upper limit is 3,361. And obviously, we're saying that's to better define our forecast. We could say that our best estimate of snowboard sales in 2010 is 3,248 units. Okay, good. We saw that. Right, that we are 90% confident that the sales will be between the 2.8 and the 3.6. Okay, this is very important, that we are most certainly 90% confident that it will be the case. It will be between these two. So this, yeah, and this is about the confidence in a forecast. Right, the alternative approach to develop and verify the regression line. Right, now that we have determined the statistical values for the regression line is presented in table 10.5, we can use these values to develop the specific values of the regression points. and further to verify the standard error of the estimate, SE. The calculation steps are shown in table 10.6. The column Y head is calculated using equation 10.3 in the inputting the constant values of A and B from the table 10.5. The total of Y minus Y head in column 5 verifies that. And obviously using the total value of the Y minus Y head in the column 6 and the last column of table 10.6. Okay, we shall look at that table and analyze it together. All right. And inserting these in equation 10 and the 8th Roman figure sort of verifies the value of the standard error of the estimate of table 10.5. Okay, so we can obviously be in a position to determine the rest of these values, like the Y minus Y hat squared. And obviously the Y hat itself is the predicted or the forecast values. How to determine? We use the regression line. So if we put in the X, we're able to get the Y hat. We put in the X, we're able to get the Y hat, and these are the values we're getting. And now we can be able to find the difference between in terms of Y minus Y hat, and then we square them. Right. And this becomes the alternative approach. Right. But as said really here, the last column of table 10.6, the last column, and inserting this in equation 10, 8th Roman figure, verifies the value of the standard error of the estimate of table 10.5. Right. So if you actually insert this in the equation 10, 8th Roman figure, right, so obviously, why are we squaring these things like the Y minus Y hat squared? Because we want to use the standard error. We want to just verify the standard error. That the standard error is as stated. What is the standard error? Okay, the standard error is 243, blah, blah, blah. Right, so, okay, 234, excuse. Okay, so we're to mention that is 234, right, which is 234, which is 234. Okay, so if it is 234, we can verify that using obviously this table here, because we take the summation of all the squares and divide by the degrees of freedom, or rather the sample size minus 2, which gives us the degrees of freedom. Okay, so yeah, we actually can always do that. If you take all these things and add them up, and divide by n minus 2, 16 minus 2, then take the square root, you're going to get the 234.18, which is 234.18. Okay, need to make sure that we have that. So that is just an alternative way to verify. That is the alternative approach to develop and verify the regression line. So we continue. The idea of the linear regression and the causal forecasting. Right, so linear regression and what we call the causal forecasting. Okay, so let us discuss the part of the linear regression and the causal forecasting. Okay, obviously this is a continuation to that, but it's not substantial. It's very, very straightforward. But we're saying in the previous sections we've discussed already. We discussed the correlation and how a dependent variable changed with time. Another type of correlation is when one variable is dependent or a function of not of time on some other variable. For example, the sale of household appliances is in part a function of the sale of new homes. Okay. The demand for medical services increases with aging population. If the population is getting old, then there's a demand for medical services. So the demand for medical services, right, increases with an aging population. So if you have older people, then they go to hospital more. They demand more medical attention than younger people. So the quantity sold is a function of price. In these situations, we say that the movement of the dependent variable y is caused by the change of the dependent variable x, and the correlation can be used for causal forecasting or estimating. The analytical approach is very similar. The more practical and the approach of using formulas, which we call the analytical approach, is very similar to linear regression for a time series, except that it is except that time is replaced by another variable. So yeah, so time is replaced by another variable at times. The following example illustrates these. Okay, so linear regression and causal forecasting. So yeah, sometimes we're not using time, we are using the aging population to determine the demand for medical services or the sale of electrical appliances in relation to this sale of this. You were saying the sale of household appliances is in part a function of the sale of new homes. If there are new homes, then you have the household appliances being sold. Okay, so we continue with this now. So we continue with this. So, and this here becomes the forecasting. Right, so application of causal forecasting, surface area, and house prices in a certain community. Okay, this is just an example. Right, so now in a certain community in southern France, a real estate agent has recorded the past sale of houses according to sales price and their square meters of living space. This information is in table 10.7. Let's analyze briefly the table 10.7 in relation to the French situation. Okay, right. So develop a scatter diagram. This is what is stated. You need to develop a scatter diagram for this information. Does there appear to be a reasonable correlation between the price of homes and the square meters of living space? Okay. Here, this is a causal relationship where the price of the house is a function or is caused by the square meters of living space. This is very important. Thus, the square meters is independent of variable x, and the house price is the dependent variable y. So the house price is y. Thus, the square meters is the independent variable x. So the more space you have, the higher the price of the house. Using the same approach as for the previous no-board example in time series analysis, figure 10.6 gives the scatter diagram for this causal relationship visually. Okay. It appears that within the range of the data given, the house prices generally increase linearly with square meters of living space. So we continue. Show the regression line and the coefficient of determination on the scatter diagram. Compute the coefficient of correlation. What can you say about the coefficients of determination and correlation? What is the slope of the regression line and how it is interpreted? Okay, we continue. We continue. Okay, the regression line is shown in figure 10 in figure 10.7. We shall look at the figure. Shall look at the figure there. But before I look at the figure, I want us to, yeah, we think the regression line is shown in figure 10.7. Together with the coefficient of determination, the relationship are as the relationships are as follows. So the regression equation, this is the regression equation. If this is the case, the square meters and the price, the surface area and house prices. So it means that if you have 100 of square meters, the house price can be like 260,000 euros in France. But if you have square meters of 125 square meters, then you have like 280,000 euros, 125. So yeah, it means therefore, if you have a larger space, then the house is more expensive than a smaller space in terms of square meters. Okay, this becomes the regression equation. So the regression equation becomes this, the coefficient of determination. So if this is the x and this is the y, we can be able to get the regression equation because we can get our a, we can get our b, and then we can use y equals a plus bx, something of that sort. And then from this, we're able to get can use this, the y hat, the predicted y value. Okay, the coefficient of determination is the r squared, and therefore we can be able to get the coefficient of correlation, which is exactly r. So for these houses, we're able to see that r is 0.8623, which is the coefficient of determination. And then now you have the coefficient of correlation, which is r. So we have the coefficient of determination, which is r squared, and then we have the coefficient of, determination is r squared, and obviously correlation is r. Okay. Now, since the coefficient of determination is greater than, okay, let's look at this analysis here. For this house, okay, we can do this, but obviously we agree that it's a long calculation. We don't need to go through this. We can use Excel, we can use our calculator to do this. Then, okay, if r is 0. Here is r. 0.9286, which is the coefficient of correlation. And then now the coefficient of determination, which is 0.8623. Okay, but we see that the coefficient of determination is greater than 0.8. So we're saying the coefficient of determination is greater than 0.8. And thus the coefficient of correlation is greater than 0.9. So the coefficient of correlation is bigger than 0.9. We can say that there is quite a strong correlation. Okay. The coefficient of determination is bigger than 0.8 because 0.86 bigger than 0.8, and then this one is bigger than 0.9. So we can say that there's quite a strong correlation. And then now we're able to look at the scatter diagram for the surface area and the house prices. So if this is the price, house price, and the area, so you can see that as the area increases, the house prices also increase in some way. Okay, if we can plot like this, okay, look at this. For the area, it's 50, 100. We just chose the scale of 50 because this was, okay, for the area, you have 100 up to 125, and then you have 200, 360, 250. So it was sensible for the area to take 50 steps of 50, 100, 150, and so on. And then for the price here, you can see there are reasonably higher prices in euros. This one is like 2,945,500 euros out there. And obviously you have those larger values there. 2.9 million appears to be, okay, there's also 5.2 million, 3.6 million, 3.8. Okay, but now you can really see something. Okay, we are concluding, please. Okay, you can really see that as the area increases, the prices increase. Okay, let's look at how these regression. So here is the regression line. The regression line for surface area. Okay, this became the regression line. Yeah, and then we have your, which is written in the Excel form. So it's the bx plus a. So the regression line is 11646.6. 6133x minus 1263749.9048, and therefore r squared is 0.8623. Okay, this is the regression line, and therefore this regression line, for example, when x is 0, then you're going to have minus y. So, okay, this line starts there. Okay, doesn't matter what you do. Okay, so this is become the y-intercept. So the y-intercept is going to be, rather the x-intercept for this is going to be obviously where x is the areas. And then now you can solve for x. And when you solve for x here, when y hat is 0, just demonstrate that. Okay, we're finishing now. 0 equals 11646.613 x minus 1263749. Okay, I'm just taking this one as it is, which came from here. And then now want to solve for this x. So solving for x is 1263749. You divide by 11646.613. Please come again.
No, I'm just repeating your formula.
Okay, thank you so much. That's fine. Yeah, thank you so much. Okay, yeah, we're getting x, but this is going to give us the x value here. Just trying to say, well, whatever it is there, but it's just the value that is bigger, like between 100 and 150. That is going to be the x-intercept. So that is where you're going to base and root your regression line when you draw it. When you sketch it, so you're going to sketch it. It's going to have its base, its intercept here, and then obviously the slope of it. Right, so obviously the slope of it is determined by this here, and as you can see, what happens that is going to have not quite that, slightly below. Okay, I'm finishing, please. Right, using free, something of that sort. Okay, so you're going to have okay, this must be a straight line, but you're going to have the regression line on average like this, but it's going to have its intercept there. And obviously, at this position, it cuts through an average, the middle of all these points here. And I think that we're going to obviously continue in our next discussion and look at more things. And it was interesting discussing these things here.